Welcome back. I'm Professor Andy Gunawardena, and today we're diving into an exciting algorithm in machine learning called naive Bayes. This algorithm is a clever and practical application of Bayes' theorem, and I can't wait to show you how it works. Let's get started. So, what is naive Bayes? Naive Bayes is a powerful yet wonderfully simple machine learning algorithm that uses probabilities to make predictions. Just like other ML algorithms, it's built on three key elements: the hypothesis function, loss, and optimization. That is, we have a model or hypothesis function. All models have loss in estimation, and the goal is to reduce the error in loss or optimization. The concept? We treat both inputs and outputs as random variables. For inputs, we have multiple features, like words in a text, each represented by a variable. The output is a single variable that represents what we're predicting, like a category or label. Our mission is to estimate the probability of that output given the input. Nice thing about naive Bayes is it is fast, easy to interpret, and highly effective, making it perfect for tasks like spam detection and sentiment analysis. Let's dive in and see what makes this algorithm so useful. As an example, let's say we want to classify documents into categories. Imagine we have a labeled set of documents to learn from. We know the number of documents in each class, and we can determine the probability of a word appearing in a document from a specific class. There's a high probability that a word like AI shows up in a tech document, right? We can calculate that probability, which tells us how likely we are to see a word like AI, given that the document is about tech. This is what we call the likelihood. Next, we can calculate the probability of a document being in the tech category by simply dividing the number of tech documents by the total number of documents. This is what we call a prior I'm. And we can also figure out the probability of a word appearing in any category, which is also a prior. With all these probabilities, the likelihood, the prior for each category, and the prior for each word, we can then calculate the probability that a given observation belongs to a specific category. We'll dive into some examples soon to see how this works in action. We start with an application for spam detection. Imagine a robot sorting emails. It breaks each email down into tiny pieces, like words or features, and learns which words are commonly found in spam emails. When a new email arrives, the robot compares its words to what it's learned. If most of the words are often found in spam, it confidently flags that email as spam. It's like a detective solving the mystery of spam emails. Now, who does the original labeling in this supervised learning example? That's where we come in. Every time we mark an email as spam, we're providing feedback. If enough people flag an email, it officially gets labeled as spam. Teamwork at its finest. The second example is about sentiment analysis. Imagine a robot analyzing customer reviews. It breaks each review into tiny pieces, like individual words, and learns which words are commonly found in positive, negative, or neutral reviews. When a new review comes in, the robot compares its words in the review to what it's learned. If most of the words match those typically found in positive reviews, it labels the review as positive. It's like a detective uncovering the secrets of customer sentiment. And there are plenty of other examples we can find just like these. Now let's just dive into some examples that we can work through by hand to really understand this process. We will start with a simple example. Imagine we have 8 documents labeled as either SAM plus or I plus. SAM plus documents contain more instances of the word SAM, while I plus documents contain more of the word I. We'll split our data set into a training set and a testing set to explore this. First, let's calculate the prior probabilities. Essentially, What's the probability of a document being SAM plus or I plus? In our training set, 3 out of 5 documents are labeled as SAM plus, and 2 out of 5 are I plus. So the probabilities are 3/5 for SAM plus and 2/5 for I plus. Next, let's compute the probability of seeing the word SAM given that the document is SAM plus. In SAM plus documents, there are 13 words in total, and 7 of them are SAM. We can do similar calculations for other words in SAM plus documents, as well as for the probability of these words in I plus documents. Let's get our hands on some numbers and see how this works. Let's dive into this example. Suppose we want to classify a document that contains the words SAM, SAM, SAM. Our goal? To figure out whether this document is more likely to be labeled as SAM plus or I plus. To do this, we'll calculate the probabilities. What's the probability that this document belongs to SAM plus? And what's the probability that it's an I plus document? By using Bayes' theorem, we can find both. Here's the trick. The denominator in both calculations is the same, so we can ignore it and focus on the numerator for each calculation. They may not be actual probabilities, they might not be less than 1, but they allow us to compare and see which one is larger. In this case, the probability for SAM being a SAM plus document is higher. So, we predict that this document belongs to SAM plus. And guess what? Our model got it right. This document is indeed labeled as SAM plus in the test set. Great job! We're really getting the hang of this. Now it's your turn to try this out. Take a look at the documents that contain the phrases I am Sam, Sam I Sam, and I Sam I. Using the same method we just practiced, work through each one to decide how it should be labeled. Remember, you can skip the denominator and just focus on comparing the numerators. Give it a shot, and when you're ready, check the comments section or open-ended questions in qubits.ai to find solutions and compare your results. Happy calculating! Now let's dive into the different types of classifications we can use in probabilistic modeling. There are 3 types of probabilistic classifiers we can work with, each one serving a unique purpose. First up, we have the random classifier. With this approach, we randomly pick a category for each document. It's a straightforward way to set a baseline for accuracy. If a model performs worse than this random classifier, it's a clear sign that it isn't learning effectively from the data. Next, we have the max classifier. This one is particularly useful when one class dominates the dataset. By assigning all instances to the most frequent class, it can yield high accuracy on imbalanced data and serve as another benchmark. If your model can't beat this classifier, it's probably not leveraging the data structure well. Finally, there's the star of the show, naive Bayes. This classifier uses conditional probabilities to make predictions, taking advantage of multiple features in the data. Unlike random or max classifiers, naive Bayes creates a more structured model, often leading to greater accuracy and insights, especially for simple or small data sets. Each of these classifiers has its place, helping us understand and improve the effectiveness of our models. Now let's dive into another fun example. Should we play golf? Let's see how we can use probabilistic modeling to answer this question. Let's imagine we've collected data over a period of time, recording details like the outlook, temperature, humidity, wind conditions, and whether or not people played golf. With this data, our goal is to predict whether someone should play golf on any given day based on specific conditions. For example, we might ask, if a day is rainy, with cool temperatures, high humidity, and it's windy, what would our Bayesian model predict? Should we play golf or not? We can also dive into questions directly from the data. Say we want to know the probability of someone playing golf on a high humidity day. By looking at all the high humidity days in our data, we find there were 7 in total, and on 3 of those days, someone played golf. So the probability is 3 out of 7. We can keep exploring different scenarios and calculating the probabilities. Let's see what insights we can uncover. Next up, let's create our frequency and likelihood tables. We'll do this by counting the values that belong to each class. Here, we'll focus on the frequency and likelihood tables for yes decisions. Let's get counting and see what patterns emerge. And here are the tables for no decisions. Feel free to pause the video, go back to the original table, and see how each of these numbers was calculated. Take your time to explore. Each value tells a part of the story. We can create frequency and likelihood tables for outlook, humidity, temperature, and windy conditions as well. Be sure to check back with the original data table to see how each of these tables is constructed. Understanding the process here is key. Each table builds on our data story. Now, the big question, should we play golf given these conditions? It's a rainy day with cool temperatures, high humidity, and it's windy. What should we do? Let's calculate the conditional probabilities. Given these conditions, what does Naive Bayes predict for the probability of yes versus no? Remember, we're ignoring the denominator since it's the same for both calculations. After crunching the numbers, we see that the probability of no is higher than yes, so the recommendation is not to play golf today. But hey, if you're feeling adventurous and decide to play anyway, it's a free country, we can just add this new experience to our data set. In conclusion, Naive Bayes is a fantastic tool for its simplicity and efficiency, but like all models, it has its limitations. Knowing when to use it and when not to can make a big difference in the accuracy and reliability of your machine learning results. One key point to remember is that Naive Bayes treats each feature independently, which can sometimes lead to inaccurate probability estimates. It may also struggle with intricate patterns that rely on combinations of features. Additionally, Naive Bayes depends on prior probabilities derived from training data, so with a small dataset, these priors might not be as reliable. So Naive Bayes is not the one-size-fits-all solution for every machine learning problem. In our future videos, we'll explore other models that can handle different types of data and more complex patterns. Stay tuned for even more machine learning insights. In the next video, we will look into implementation of Naive Bayes with a real data set. So for now, stay tuned and we will see you later.